Continuing with the static timing analysis, and in particular we're talking about the slack, and that's the required arrival time at a node minus the actual arrival time of the node. So that's the latest time a signal can transition to the latest possible transition time. And by convention, as we saw before, the AAT is defined at the output of every node. So a negative slack at any output means that the circuit does not meet its timing requirements, and a positive slack at all of the outputs means that the circuit does meet its timing requirements. So following on from the graph that we saw previously, we can complete the slack at each node on a graph, and it's relatively easy to calculate since we know the RAT value and the actual arrival times. We just do a simple subtraction to get our slack values. So knowing the slack values helps us determine where the most help is needed in trying to meet the timing constraints. And the STA, for example, can be influenced by place and route. So you put most of your attention on where the minimum slack is. So that's a negative number, so it's a large negative number. In effect, you allow revisiting the steps to redirect attention to critical paths, and hopefully you make the circuit a little bit quicker. Perhaps the delay on a line is a little bit less than it used to be. So with respect to timing optimization, critical paths or critical nets are signals that have negative slack, while non-critical paths would have positive slack. So timing optimization is a process by which negative slack is increased to achieve design correctness. So i.e. it was a negative number before, maybe -2, and you want to make it -1 or 0 ideally. And positive slack is reduced to minimize over design and recover power and area. So if you have excessive positive slack, you can make the circuit perhaps a little bit smaller or less powerful than it was before. As a consequence, it's going to consume a little less power and consume a little less area. Physical synthesis is a collection of timing optimizations that are used to fix negative slack, and it basically consists of creating timing budgets and performing timing corrections. So a timing budget would include allocating target delays along paths, and that might happen during the placement and routing stages, and it could also be during the timing correction operations. Where we're going to put most of our attention is the timing corrections, which include things like gate sizing, buffer insertion, and netlist restructuring. So those are techniques that you'd use to improve the negative slack. So we're going to look at gate sizing first, and we're going to look at arbitrary gates of having 3 different sizes, A, B, and C, where the size of gate C is bigger than the size of gate B, which is bigger than the size of gate A. So these are logic gates, not individual transistors. So a gate with a larger size has lower output resistance, and size in that case means in the case of our planar FET, it would be the width of the transistors involved in the gate, or the number of fins if it were a FinFET type of structure. So when the load capacitances are quite large, it might be the case that the larger gate is going to have a lower delay. The gate with a smaller size might have a higher output resistance. And when the load capacitances are very small, which is a consequence of the fan-in of the drivers themselves, the delay on the largest gate might actually be larger than the delay on the smallest gate. So that part's perhaps a little bit counterintuitive, but remember, the gate itself presents a larger load to the gate that's driving it. So here's a scenario which is given for gates of various sizes, A, B, and C. So A was the smallest gate, C was the largest gate, and depending on the load capacitance, one of these types of structures will dominate. So if you're at a 3 femtofarad load, you see that gate C was 28 picoseconds, but if you had a 0.5 femtofarad load, you see that gate A was the fastest at 15 picoseconds, and that's sort of what that graph represents. So this is some of the rationale for that. I'm not going to go over it in any great detail other than to bear in mind that those calculations were based on sort of a load-dependent delay, and that was the first scenario we looked at. And if the load capacitance was small, it's the intrinsic delay that's going to dominate. So that again is taken from that physical design, VLSI physical design chapter. Anyway, here's an example where gate size can definitely impact the slack, and this will be identified by doing your slack calculations so that you know that you have negative slack at that gate. And what you could do then is you would change the size of the gate. So In this case here, you have an option of going to the smallest gate or perhaps the largest gate, and you know that the load that it was being driven was, in this case, 3 femtofarads. So you'd look up the delay, and it says 40 picoseconds from the graph. Here, over here, the capacitance is the same, but you use a much larger gate, and you see that the delay is only 28 picoseconds. Again, that was extracted from the graph. So resizing gate V from gate A to gate size can achieve a lower gate delay. Other things that you can do is you can use a buffer, and that's a series of 2 serially connected inverters. So it's no function change, and that's what it looks like schematically. 2 inverters, and you draw on a buffer now. You can improve delay by speeding up the circuit. Perhaps you're driving a long line, so if you partition it into sections, it might be faster. Or it could actually be used as a delay element, which would also improve delay, and we'll look at some examples of that. Change transition times and shield capacitive loads from a gate, and we'll look at examples of those. Some of the drawbacks, of course, when you introduce buffers, you have an increased usage area and you have increased power consumption. And what that relates to is, the heat that the device is going to be generating. So here's an example of buffering. We have a load of 5 femtofarads. We just add those up there. And we would just extract from that graph previously, since it didn't go up that far. But if you extract it to that graph, you'd see that it went to 45 picoseconds. So one of the scenarios might be then to use a buffer. So the initial gate is now, instead of driving 5 femtofarads, it's only driving 3 femtofarads. So you'd look at what its delay is going to be. It's 33 picoseconds. The buffer that you introduced is also driving 3 femtofarads, and it's of size B. So you'd look up its delay, and it would be 33 picoseconds. So the delay to here is actually worse than it was previously at 66 picoseconds. But the delay out here to C and D is actually much better. It's only 33 picoseconds. And this would have been the scenario where C and D, or E and D rather, would have been on the critical path. So you've actually improved the timing of parts of the circuit, perhaps at the expense of others. You can also look at netlist restructuring, which changes existing gates but doesn't change functionality. And some of the changes could include cloning, so that's duplicating gates, redesigning a fan-in or fan-out tree, changing the topology of the gates, swapping communicative pins, so that's where the order didn't matter. Gate decomposition, you can change a structure such as AND OR to NAND NAND. And Boolean restructuring is just applying Boolean laws or formulas to change the circuit gates themselves without changing the functionality. And you can also do reverse transformations to those, which would be downsizing or merging. And we'll look at a couple examples of that as well. So here's an example of cloning, where you'd reduce the fan-out capacitance. Here's our initial scenario where we had an AND gate of size B, and it had a 5 femtofarad load, and you look that up on the table and you see it's 45 picoseconds. So the gate is cloned. One is a little bit smaller, so now the delay to do D and E is 30 picoseconds. Delay to F, G, and H, since it's only a 3 femtofarad load with a larger gate, is 33 picoseconds. So we cloned the gate and made it a little bit larger. You can also reduce the downstream capacitance rather. And here's an example of it where we have this gate having these 5 lines, but 2 of them are very long, and they're going over to some portion of the chip, which are again close together. So basically we clone the gate. The load seen by this one is reduced. The load seen by this one is reduced, and the 2 long wires effectively become 1 long wire. So in this scenario, maybe the total capacitance out here was 7 femtofarads. If it's 1, 2, 3, let's say these long wires contribute 2 each. Then in this scenario here, we have this gate looking at 3 femtofarads and this gate looking at 3 femtofarads for a total capacitive load. You can restructure the netlist, and that can also be used to change the actual arrival times. So in this particular case, if the actual arrival times worked out to be 6, you could restructure the inputs. Again, you have to know what these actual arrival times are before you can do the restructuring. You'd see that the arrival time on the output is 5. You can redesign the fan-out trees and change the delays on specific paths. So in this particular case, 2 buffers were introduced, and then what happens is the load is redistributed to this buffer and removed from this buffer, so that this gate looks like it's looking at a little less capacitance. So in that case, we had a shorter delay on path 1, but perhaps at the expense of an increased delay on path 2. But if we had slack to burn on path 2, that's not a problem. And if we were trying to reduce the slack on path 1, then that would have been an effective trade-off. Swapping commutative pins where the order doesn't matter can also change the final delay, much like we saw in the previous examples. This permutes the inputs, but the functionality stays the same. Whereas we had an actual arrival time of 5, now we have an actual arrival time of 3. Gate decomposition can also change the general structure of a circuit. In this particular case, went from AND OR. So if we put those two balls there, send one that way, send one that way, we end up with a NAND structure. But it may be that we were worried about the fan-in on this gate, so we've actually increased the number of logic levels, but reduced the fan-in on any particular gate. So 3-input gate was reduced to 2 2-input gates. So there might not be a problem if you're looking at these small number of inputs, but it could be the case if the number of inputs were much larger than that. Boolean restructuring uses the laws or properties of Boolean logic. For example, here's the distributive law to change circuit topology. There was an example before where we had our actual arrival times being 6 at the output of this structure here. But if we just restructure the logic, we end up with actual arrival time on X, which is 5, and actual arrival time on Y, which is 6. But maybe we didn't have to change 6, but we did have to change Y. And this again would depend on what the actual arrival times were for the inputs on that small part of the circuit to where we were trying to reduce the slack. So most of the proceeding was pretty low level and not likely to be encountered as synthesis tools automate more and more of these methods. It's important to remember that very little of this is done by hand. A static timing analysis tool would likely generate a report to be used to augment better place and route, for example, or gate sizing or logic itself. Also bear in mind that ASIC and FPGAs will have a different emphasis with respect to the static timing analysis. And at that point in time, we'll take a brief break.